Welcome my dear students to We Teach. Today we are in a session to discuss the closure properties of regular languages. In this video we will discuss the properties of regular languages. So how and what they are. Closure properties on regular languages are defined as certain operations on regular languages. That means if the operations are done on the regular languages, we can consider whether they are following the closure properties or not, which are guaranteed to produce regular language. That means if any operation is done on the two languages, then the resultant also should be there in the regular form. Then we can say that it is under closure. Closure properties refers to some of the operations on languages as follows. See, the first one is the first operation on is we are considering as example as L and M are the regular languages. So on them we are going to see the properties. The first property is Kellen closure. So under this, RS is regular expression whose languages are L and M, and R star is a regular expression whose language is also the L star. That means the language that is generated in the closure. So the first one is satisfied. Next one is positive closure. RS, that means the language that is the grammar or the production which is produced on the language that is RS, whose regular expression as the language as L and M, where we are not considering the R star, is a regular expression whose language is L. Next one is complement. The complement of the language L with respect to the alphabet, then such that the language L, that means ML, and since L is surely the regular complement, means L dash is the regular complement of the given language as regular. Next one is reversal. The given language L and LR is the set of strings whose reversal is in L, where example consider as 0, 0, 1, 1, 0, and the reversal LR can be given as 0, 1, 0, that is the reversal, and 0, 0, 1, that is the reversal, which is also there in the form of regular language. Let E be the regular expression for L, which we show that the reversal of E to the provide a regular language L dash for. So the next one is complement. The complement of a language L. The next one is union. Let L and M be the languages of regular expressions R and S. Then respectively the R plus S, that is the union of two regular expressions whose language is L union M. So automatically the generated languages are in the union, that is under the regular expressions. So we can say that the generated language is also the regular language. Next, intersection. L and M be the languages of regular expressions R and S respectively, then the regular expression whose language L under intersection M, then we can say that we can define it as let A comma B the DFAs whose languages are L and M respectively, construct the C, then the production automata, that means product of automatas A and B, make the final state of C with a pair of consisting final states of both A and B. That means both are having the final states as both and B. Then we can say that the intersection of the DFAs is under the regular languages. So we can say that intersection also follows the property. Next one is set difference. Let L and M be the regular languages so that L minus M, strings in L but not M. Now consider A and B be the DFAs whose languages are L and M. That means based on the language L and M, we define two DFAs as A and B. Then we are constructing C. That means the product of A and B makes the final states of C. Then the pair of A states is final, but B state is not final. When we consider the same concept in the intersection, there make a notation that both the final states of A and B are common, then we can say that they are under regular. Here, under the difference rule, only the final state of A is considered, not the final state of B. So we can say that it is the difference operator on both the languages. Next one is homomorphism. A homomorphism is an alphabet, that means a function that gives a string for each symbol in the alphabet. For example, h of 0 is equal to AB and h of 1 is equal to AN. Extend to the string as h of A to AN is equal to h of A1, h of AN. For example, h of 0, 1, 0, 1, 0 can be defined as like this. Next, if L is the regular language and H is the homomorphism on its alphabet, then H of L is defined as H of homomorphism, that means on the words with respect to word belongs to the language, where it is also a regular language. How we can give the proof? Let E be the regular expression of the language L. Apply each symbol on E of the language resulting regular expression RE of HL. The next one is inverse homomorphism. As we have seen, the first one has the homomorphism, it is the inverse of that. Let H be the homomorphism and L is a language whose alphabet is the output of the language H. That means L is equal to W such that H of W is in L. There are few more properties like symmetric difference operator and prefix operator. Substitution of these are closed under closure properties of regular languages. So these are the properties, that means closure properties on regular languages. And the next properties are decision properties. Approximately all the properties are decidable in case of finite automata. See what are they? The first one is emptiness, non-emptiness, finiteness, infiniteness, membership and equity. So these are the important on the context of examination. So these are explained as follows. See, the first one is emptiness and non-emptiness. See how we can define these. Select a state that cannot be reached from initial state to initial state and delete them. So that means removal of unreachable state. Next one, if the resulting machine contains at least one final state, so then the finite automata accept non-empty language. Third one, if the resulting machine is free from final state, then the finite automata accepts empty language. So consider these points. The first one is select the state that cannot be reached from initial state and we need to delete. Next one is the resulting machine contains at least one final state, so then the finite automata accept non-empty language. Third one is if the resulting machine is free of final state, then the finite automata accepts empty language. Now the next one is finiteness and infiniteness. How we can decide the finiteness and infiniteness? First step, select the state that cannot be reached from the initial state and delete them. That is the first step. Second step, it is as the previous one. Second step is select the state from which we cannot reach the final state and delete them, that is the dead states. The previous one is unreachable state. Both are having the same result. Step 3. If the resulting machine contains loops or cycles on the finite automata, accepts infinite languages, which accepts infinite languages. Step 4. If the resulting machine do not contain loops or cycle, then the finite automata accepts infinite languages. Infinite languages. These are the 4 steps under finiteness and infiniteness. Next one is what is membership? What is the membership? Membership is a property to verify the arbitrary string is accepted by finite automata. What is meant by arbitrary string? It is the member of language or not. That is considered. Next one is let M be a finite automata that accepts some string over an alphabet, and let W be any string defined over alphabet. That means with alphabet. If there exists a transition path M which starts with the initial state and ends at any one of the final state. Then the string W is a member of M. It is very clear. Otherwise, W is not the member of M. So, this is how we can consider the given W, that is the string defined with the alphabet. That means W is the string that is defined with the alphabet from the language, and there exists an initial state and there exists a final state. Then we can say that W is the member of M. W is the member of M. If it is not there like that, then we can say that it is not the member. This is how we can define the membership. Next one is equality. Two finite automata, that is M1 and M2, is said to be the equal if and only if they accept the same language. That means minimize the finite automata and terminals DFA will give unique state, then we can say that equality. Once again, have a look onto the properties like this. They are emptiness, non-emptiness, finiteness, infiniteness, membership and equality. Where we can define the emptiness and finiteness common way, finiteness and infiniteness in another way, where the membership and equality in two different ways. So these are the decision properties that we can consider on the language and on the strings that are defined under the language. So these are the closure properties and decision properties of a regular language. Thank you so much.